Okay, so we learned about the wave-particle duality of light, how light can behave as a wave, or light can behave as a particle. And we can use that to our advantage as physicists. We can say, okay, it's going to be more useful to think about light behaving as a wave, like in this circumstance, or light behaving as a particle in this circumstance. Just how you need to use it. There's specific applications of it, but that's further than what we need to worry about in our class. So scientists had known about these spectra since the early 19th century, and they've been used to identify elements. For example, helium in the sun. But nobody could explain why they showed up. Why was it happening? And in the 19th century, early 19th century, seeing helium, seeing that fingerprint for helium, meant that there was this new element that did not exist anywhere else except for on that sun. Because by the time scientists had discovered helium on the sun, they still hadn't come across it on Earth. In 1913, Danish physicist Dr. Niels Bohr comes along. He realized electrons could only be at specific energy levels around the atom. You're familiar with this diagram, whether you've taken chemistry or not. You know this is the nucleus, and you know these little dots surrounding the nucleus are the electrons. There are better, more accurate models out there in how electrons behave. We once thought it was electrons never existing, and then once we realized the electrons, then we said, well, okay, what are they doing? And then Niels Bohr puts them on these discrete energy levels, these separate, specific energy levels around the atom. And that becomes useful for us because that's how we identify what elements are present in a given spectra. So we can say the energy of the electron can exist in a number of states. N equals 1, N equals 2. So you can see as we're going out radially, we have 1, then 2, then 3, then 4, and so on. Well, if we take these concentric circles, and we have N equals 1, N1 here, this is the ground state. This is the lowest energy that the electron is capable of having. So this is just passed out on the couch, can't move, no energy at all. As the electron becomes ionized or excited, then it's capable of jumping up these shells. And it's kind of hard to visualize here. So if we took N1 and we set it as the base, and rather than having these concentric circles that's getting farther and farther out, we can have the base N1 here, we can have the next energy level up, N2 here, N3, N4, and 5, and so on. When we do that, we get the energy level diagram. The energy level diagram according to the Bohr model for the hydrogen atom. We'll get to that, but let me walk you through this energy level diagram. We have the energy in electron volts over here. The ground state. Electrons can't have less energy than this. Negative 13.6 electron volts. N2, N3, N4, and 5. As you grow higher in the energy levels, then you get closer and closer together. All the way up to energy equals 0. So how can that be? All right, so the energy that we're talking about for an electron, there, we've got an electron. It's sitting at N equals 2. The energy that we're dealing with over here is it going to be kinetic energy, potential energy? What do you think? Well, remember the Bohr model says the nucleus is here and the electron is here. If the nucleus has protons inside of it, is there an attraction here? Yeah. So it's acting very similarly to gravity. So the electrostatic force is going to get less and less and less as you get further away. And as you get closer to infinity, eventually your attractive force becomes 0. Or your gravitational potential energy becomes 0. Or your electric potential becomes 0. So the same thing is happening. Right here, we have the most potential energy for that electron to go towards the proton living in the nucleus. Once that electron goes all the way up here, and it reaches energy level of 0, that means it's gone. It's never returning back to the atom. That's not what we're talking about here. We're talking about just electrons that are stuck to the atom because of the attractive force of the proton to the electron. All right, so the electron jumps up into a higher state other than ground. That's called an electron, an excited electron. Ionized. Same thing, ionization. You're exciting the electrons. They're jumping from N1 to N2. Eventually, it's going to get tired, and it wants to be back on the couch, passed out, right? Well, when it does that, where does that extra energy go? An electron is in an excited state, can make a transition to a lower state. Thus, an atom in state n equals 2 can go to n equals 1. An electron jumps from orbit 2 to 1. So from here to here, whee! I think about it as it's taking in a whole bunch of energy, a whole bunch of food, gets excited, having fun, and then crashes, passes out, and then poops out a single photon of light. That extra energy that has been taken in, usually through an electrical current, extra electrical energy has been absorbed by the electron and then has to be sent back out. And when it does that, it releases it as packet of energy that is a photon. Gets excited and then crashes and poops out a photon. Energy of the photon is equal to the difference in energy between the two states. It is equal to h times f. H is Planck's constant. We'll talk more about that and what its numeric value is. F is the frequency. E is the difference in energy between the two states. So if we went from 1 to 2, we need to figure out what is this energy level here. The opposite happens when a photon of light is absorbed. So this is the absorption, creation of the absorption spectrum. E equals hf, whatever the frequency of light coming in. Frequency can be found with the C equals F lambda. Data booklet time, talking about all of these equations. Let's clear it up. We have E equals hf, and we know that V equals frequency times lambda, or C for light waves. So combining these two, we get lambda equals h times c over E. 1 electron volt equals 1.6 times 10 to the negative 19 joules. When we're talking about this change in energy here, we're talking about normally electron volts. But you have to be careful, watch your units. A lot of times questions will switch it up on you and ask you it for the answer in joules.